8.5 lesson 1, partial fractions. So we begin with adding these two rational expressions. How do you add two rational expressions? You need a common denominator. So we multiply each rational expression by a form of 1, and our common denominator is going to be 2x plus 1 times x minus 1. The numerator of our first rational expression becomes 3 times x minus 1, and the numerator of our second rational expression becomes 2 times 2x plus 1. We can distribute and multiply what we have in the numerator, and then we can combine like terms. So we have 3x minus 3 plus 4x plus 2, all of that over 2x plus 1 times x minus 1. And when we combine like terms in the numerator, we will have 7x minus 1 over 2x plus 1 times x minus 1. If you multiply the two factors in the denominator, then the final answer would be 7x minus 1 over 2x times x is 2x squared. And then you have 1x minus 2x, which is negative x. And then 1 times negative 1 is negative 1. So this is how we add two rational expressions. We need a common denominator, and we proceed as we just saw. Partial fraction decomposition is the opposite problem. In partial fraction decomposition, you start with what we have at the very last line of our work that we just did. So you start with the rational expression. For example, you would start with 7x minus 1 over 2x squared minus x minus 1. And in partial fraction decomposition, your objective is to end up with 3 over 2x plus 1 plus 2 over x minus 1. How do we do that? That's a part of our lesson for today, and that part of our lesson is actually pre-calculus rather than calculus. It is called partial fraction decomposition. Why do we want to do this? The reason why we want to do this is because you may have an integration problem where the integrand, for example, is 7x minus 1 over 2x squared minus x minus 1. If you are able to rewrite the integrand by doing partial fraction decomposition, then your integration problem can be rewritten as 3 over 2x plus 1 plus 2 over x minus 1. And this is actually something that we know how to integrate by using something called the log rule for integration. You can use something called the log rule for integration and integrate. And that's why we want to do that. So we will go ahead and show you how to do the integration, and then we will go back and talk about how you can go from this step to this step, which is called the partial fraction decomposition step. That is actually pre-calculus. To do the integration, we're going to use something called the log rule for integration and use substitution as needed. And again, we begin here and we use partial fraction decomposition to write the integrand as a sum of two partial fractions. And our lesson will include how we do that. But once we have that, what is the point of doing this? The point of doing this is once you have the partial fraction decomposition, it is easy for you to integrate by using the log rule for differentiation. So we'll actually talk about the benefits of doing partial fraction decomposition first, and then we will show how to do partial fraction decomposition. So here's the main benefit. You're able to let u be equal to 2x plus 1 here. Then du will be equal to the derivative of 2x plus 1 with respect to x is 2, so 2 dx. And then you can integrate as follows. So you will have 1/2 times du is equal to dx. So now you are able to change variables. You can factor out the 3 from the numerator, and then 2x plus 1 is u. dx becomes 1/2 du. You can factor out the 1/2, and this is what you'll have. And you can also do a u substitution for the second integral. I'll just use a different color. I'm using the same letter u, so it might be confusing, but I'm using a different color to help you see that this is only for the second indefinite integral. Let u be equal to x minus 1, then the differential of u will be equal to dx. So now you're able to change variables, and you will have, I factored out the 2 from the numerator, dx becomes du. So again, I'm just using different colors to help me distinguish between the two u's. So now for the first integral, I will have, for the antiderivative, natural log of the absolute value of u, which is 2x plus 1. And for the second indefinite integral, I'll have 2 times the antiderivative of the indefinite integral of 1 over u du is natural log of the absolute value of u. In this case, my u substitution was let u be equal to x minus 1, and then I have plus c. So that's my antiderivative for this problem. And this is the reason why we want to do partial fraction decomposition. So how do we do partial fraction decomposition? Let's discuss that, and then we'll take a look at a couple of additional examples. So you can see that for 8.5 lesson 1 partial fractions, our objectives are: 1, you will know that a rational expression may be decomposed as a sum of partial fractions, as we've just seen, and that the form of the partial fraction decomposition is determined by how the denominator of the rational expression is factored. And there are different forms of the partial fraction decomposition that you may have. Today we're only going to look at one of those forms. You'll be able to find the partial fraction decomposition for a rational expression whose denominator factors as a product of two linear factors. So that's the only one that we will consider today. And in fact, for the AP course, that's the only one that you're responsible for. But there are others, and we'll take a look at a couple of them in the next couple of lessons. But the one that we're focusing on today is like the example that you saw preceding this, where the denominator factors as a product of two linear factors. If that happens, what form of the partial fraction decomposition will you have? We will discuss that today for this particular case, and we will look at other cases later. Once you do that, you will be able to use partial fraction decomposition with linear factors to integrate rational expressions, as we just saw. Vocabulary is partial fraction decomposition, and we also have other vocabulary: rational expression or rational function, and partial fractions. And in the process of finding the partial fraction decomposition, we'll see something called the basic equation. So let's take a look at objective 2. You'll be able to find the partial fraction decomposition for a rational expression whose denominator factors as a product of two linear factors. So we'll go back to the problem that we began with, which was, of course, adding these two rational expressions to get 7x minus 1 over 2x squared minus x minus 1. But in partial fraction decomposition, this is what you start with, and how do you end up with the sum of the two partial fractions? That's what we want to discuss now. And in doing so, we will have to review some pre-calculus. And why do we do this? We already talked about that, so we can do the integration, and we've actually gone ahead and done that already. The first step in partial fraction decomposition is to factor the denominator. So in this particular example, the denominator factors as 2x plus 1 times x minus 1. The second step is to write the form of the partial fraction decomposition. And again, that depends on how the denominator factors. Today we're only considering what happens when the denominator factors as a product of two distinct linear factors. Distinct means they're not the same. Linear means x is raised to the first power in each factor. So when you have the denominator factor as a product of two distinct linear factors, this is the form of the partial fraction decomposition. You'll have some constant over one of the factors plus some constant over the other factor. And our objective now is to figure out what these two constants should be, so that what we will have here will be equivalent to what we had originally. And of course, as you can see, A should be 3 and B should be 2. But the question is, how would you find that if you didn't know? The problem we have is this. Here's our original rational expression. We'd like to find the values of the constants A and B so that the sum of the partial fraction decomposition will be equivalent to our original rational expression. In other words, we want to find the values of the constants A and B so that the equation that you see here will be an identity. In other words, the two sides will be equal for any value of x when you have the proper values for A and B. So the way you will find A and B is by assuming that you have an identity and working backwards to find the values of A and B. So if we assume that we have an identity, what that means is you can substitute anything for x and the two sides should be equal. But before we do that, we're going to multiply both sides of the equation that we have here by what we call the least common denominator, which is just the product of these two factors. So when you multiply the left side of the equation by 2x plus 1 times x minus 1, and the right side of the equation by 2x plus 1 times x minus 1, you get what we call the basic equation. On the left side of the equation, the LCD will actually cancel with the denominator because the denominator factors as 2x plus 1 times x minus 1. And you'll just be left with 7x minus 1. On the right side of the equation, you will distribute the LCD to each partial fraction. And when you distribute the LCD to the first partial fraction, the denominator will cancel with the 2x plus 1, leaving you with the numerator a times x minus 1, the other factor from the LCD, because 2x plus 1 canceled with the denominator. And when you distribute the LCD to the second partial fraction, the denominator x minus 1 will cancel with x minus 1, leaving you with b times the other factor from the LCD. We call this the basic equation. And as we discussed, we assume that this is an identity and work backwards to solve for A and B. So assuming this is an identity, you can substitute any value for x, and the two sides would be equal. So to solve for A and B, you want to choose a value of x that would make one of the terms equal to 0. So if you choose x to be 1, then the term that I circled in red will become 0. So let's go ahead and do that. So we're going to let x be equal to 1. And if x is 1, you will have 7x minus 1. 7 times 1 minus 1 is equal to, for the term that I circled in red, 1 minus 1 is 0, a times 0 is 0, and then I'll have b times 2x plus 1. 2 times 1 plus 1. So 7 minus 1 is 6, and 2 plus 1 is 3. So 6 is equal to 3b. So 6 divided by 3 is equal to b. So b is equal to 2. And then if I let x be equal to, now we want to make the term that I'm circling in green 0. So if I let x be equal to negative 1/2, 2 times negative 1/2 is negative 1. Negative 1 plus 1 is 0. So I'll let x be equal to negative 1/2. So now on the left side I have 7x minus 1. So 7 times negative 1/2 minus 1. On the right side, for the term that was circled in red earlier, I'll have negative 1/2 minus 1, which is negative 3/2. So I have negative 3/2 a. And I can solve for a now because the term that I circled in green, when x is negative 1/2, will be just 0. So now I have negative 7 over 2 minus 1 is equal to negative 3 over 2a. Negative 7 over 2 minus 1 will be negative 9 over 2. And you can now solve for a by dividing both sides of the equation by negative 3 over 2, which is the same as multiplying by 2 over negative 3. So that will isolate a when you multiply both sides of the equation by 2 over negative 3. And you'll get a is equal to, so 2 and 2 will cancel, and negative 9 divided by negative 3 is positive 3. So a is equal to 3, b is equal to 2. So now that we have found the values of a and b, what that means is you can come back to this step here, and you can replace a with 3, and you can replace b with 2. And what that means is you're able to rewrite the integrand from our problem as a sum of two partial fractions. And what that does is basically, we just went over the question mark that I had left here earlier. We just talked about how to go from a rational expression to a sum of two partial fractions. And the whole point of doing that is what you see on the screen right now, where we can solve for each indefinite integral by using the log rule for integration. Today we looked at writing the partial fraction decomposition for a rational expression whose denominator factors as a product of two linear factors. And once you do that, you're able to integrate using the log rule for integration.